everybody. Can you all hear me? No dogs, that's good. Yep, I'm Katie, and for the last 6 years I have been a spacecraft engineer, specifically a thermal analyst. Anybody want to guess what that is? See your faces, everybody's looking worried for when I start to ask somebody. Anybody want to volunteer? No? Ideas about thermal? Shout out, it's good. What's thermal mean? Heat, that's good. Analyst? What do analysts do? Pardon? Data, yeah. So basically, my job as a thermal analyst was generating data to understand how heat moves around on a spacecraft. The purpose of that is to keep spacecraft within a safe temperature. So I've done loads of talks about how that kind of thing works. This is my first ever one about software type things. And as you may have guessed from the part where I went software type things, I'm not actually that great about all the different software stuff. But what I can tell you about is what that looks like within the industry, how the software is going to be used by engineers, and a lot of the different challenges that we come across. So if you have questions as we go along, please do ask, and hopefully I will try and answer them in a way that actually makes any sense. So does anybody have any idea what this spacecraft is? No, that's fine. So this is Solar Orbiter. It's due to launch in the next couple of years. They keep on sliding. These things, it turns out, spacecraft really hard to design. So it was due initially to launch last year. So it's very, very imminent. And this is actually an artist's image of a thermal map. So that is actually one pretty decent use of data that engineers produce, is actually these things are nice for us to show to our customers. So yeah, we can see on the front of the heat shield here, we're getting actually above 500 degrees. And on the back here, it's nice and cold, minus 100. What sort of temperatures does spacecraft like to be at? Good, sea of blank faces, that's perfect. What sort of temperatures do you like to be at? Minus 50? No? Maybe minus 10 if you've got a good coat and stuff, a couple of jumpers. Not overly pleasant, but possibly manage? No? You're not keen on cold? Okay, well, I prefer cold, so at minus 10, I'm all right with that. But like, what's the upper limit that you're happy working in? Maybe working, as in operating, walking around and being on, maybe even on holiday, something. 25, that's the kind of temperature I'm after. 30, maybe pushing it at 40 if you had to, if you can find some shade. Pretty much, that's everything that a spacecraft likes to run at. Between minus 10 and plus 40, we've got 500 degrees on the front of this heat shield. So that was what my job was mapping how the temperature develops, what the gradients look like across the spacecraft, and then supporting the design to actually make sure that we can get those temperatures, the units within operation temperatures. So we would have an architect, they come up with the grand master plan, the whole design, and then we go, yeah, okay, that sort of works. You need to have a bigger gap there. This is going to have to be thicker. Maybe use this material, paint that a different color, that sort of thing. So that's where the analysis comes in. I managed to flick all the slides straight away. So I've kind of tried to do a little bit of a exploded diagram of a spacecraft. Anybody know this one? See, I do this for teenagers who are usually mad about space, so they can tell me straight away all of the different ones. They can even tell me when I've got them wrong. So this one here is Gaia. This great big round thing there is essentially a parasol. It's a great big sun shield, and that's to help keep the temperature of everything behind the sun shield pretty even. And that is around 30 meters in diameter, is that round section, as an idea for scale. Gaia is the billion mission. It's billion pounds to design, test, build, launch, and get it up there. Billion pixels on its cameras, and it's taking a census of 1 billion stars in the Milky Way. It's the first of its missions in terms of stability. On its requirements, it's got a silicon carbide bench. I'd be very surprised if anybody decides to do that again for a space mission, because silicon carbide is awful to work with, and it's incredibly heavy. So the reason that they have that kind of stability requirements is to get those incredibly fine measurements. it has stability requirements of 14 microarc seconds. Doesn't mean anything to anybody, does it? So as a comparison, that is the same as being able to see a hair from 200 miles away or being able to see a button on the moon from Earth. And that's what Gaia can do, and it's taking a census of 1 billion stars. So its stability requirements to be able to manage, to be able to point all those billion pixels accurately enough, to be able to take that kind of data is it's a bit of a challenge, and thermal is one of the biggest drivers for that. Have any of you come across the idea of thermoelastic distortion? You probably have. I reckon you all have. If you have a lump of metal and then you heat it up, what happens to it? It expands. Brilliant. And how about if you cool it down? Contracts. Ta-da, thermoelastic distortion. That is it. The problem is when you start doing funny shapes and you start putting heat in from different sides, that you're starting to change the shape of your structure. And if you start changing where the heat is coming from, over time you're also changing the shape of the structure in real time, and that's where the stability requirements come in. And that's where software is really starting to give us much more capabilities. So what I've got here is the exploded diagram of Gaia. We've got thermal blankety things. Basically, that job was mostly making things shiny, as you can see from the nice picture. You're going to have some solar arrays. They're actually on the back of that sun shield, because that sun shield faces the sun. So we're going to have some power for missions like Cassini-Huygens, and for Voyager, they were actually nuclear missions. And then you've got some kind of payload. That's your instruments. If it's telecommunications, that would be your actual part that's going to be receiving your TV signal, radio, whatever that is. And then you've got a bus, which is also known as a service module. That's all the stuff that you need to be able to have a spacecraft. So that's going to have things like power distribution units. It's going to have batteries in there. It's going to have data handling units. We're going to have to be able to talk to the spacecraft and to also be able to extract the data from the instruments that we've got up there. And you'll always have some kind of propellant. Every spacecraft has those things on them, unless you're talking about the very tiny CubeSats, but they're their own game. So we all use different types of software. In thermal analysis, we're using lumped parameter. The mechanical guys for the whole structure, they use finite element. But because of thermoelastic distortion, we actually need to have those software that talks to each other. That's an in-house built piece of software. Usually, they're not actually done on the same types of software. We're going to be routing all of the data through there and the power. So the electrical guys have their stuff, but actually, who's ever sat with a laptop on their knee for too long? Or been on the phone for a bit? What happens to it? It gets hot. So yeah, you put power through anything, it's going to get warm. So guess who needs to know about what on earth the electrical guys are doing? Back at thermal again. So all the different disciplines are talking to each other. And the contamination guys need to know what's going on there. So if we decide to make everything very shiny and very cold on the outside, anybody who works in contaminations wants to know what's happening there, because everything goes from hot to cold. So if you've got any dirt at all in the spacecraft, if you warm that part up, that's great, you can make it clean, but where's it going to go? It's going to go to your coldest part, and usually that's your instruments, so you're going to have a problem there. So they're the sort of software within industry, how that looks like. But actually, this is more than just, say, 5 or 6 people. This will be a couple of hundred people on one site for the main part. You'll maybe have a couple of hundred people working on the different instruments, and you're very likely all based in different countries on different types of software and probably in different languages. This is my very first mission that I ever worked on. This is EarthCARE. We've got a Russian launcher, so we need to speak to the Russian guys to understand what their temperature requirements are going to be, and we provide them with a model. As it is, I have no idea what the launchers are actually making their computer models in. We delivered that model as an Excel spreadsheet. It does exactly what it needs to do. So that was just a whole series of coordinates and the temperatures at various different points throughout the launch flight that were our temperature predictions. And that's what they gave us, and we had to then plug it into our model to work on that. And then we also had a cloud profiling radar. That's an instrument that came from the Japanese space agency, JAXA. Again, don't know what they're working in. It looks something similar to what NASA use, which is Cinder. And because the documentation didn't come across in English, we also didn't have whatever it was that they were working in, so we had no user manual for that, and it was a case of, good luck, you know what it's meant to look like. See what happens there. So that's kind of the logistical fun. How do you start and transfer data? How do you make it succinct? So I was working on this 6 years ago. EarthCARE model was around 8,000 nodes, so calculation points for the whole of the thing. That includes any models that come to us from the instruments. The JAXA full model of the cloud profiling radar, that big dish on the top, their original model was 3,000 nodes. So I've only got 5,000 nodes then for the rest of the spacecraft. It's not generally how we work. They give us a reduced model of around 150 nodes. And that's going to be good enough for us to predict what else is going on the spacecraft. And then we can give them good enough detail to go back into what they need to have for their interfaces. So that's kind of an idea as to how the different disciplines tie into one another. And then, actually, this is the kind of software that we use. Thermal software doesn't look as pretty as mechanical engineering software. Has anybody here done mechanical engineering? Excellent. Anybody done any kind of engineering software stuff? We've got one in the corner, yeah. So if you have engineering models, usually you will have CAD. So somebody's drawn a very lovely, lovely electronic picture of everything that's on that spacecraft. Great. Mechanical guys need that. They push that straight into their analysis, and the computer program the software that they're using will actually do whatever meshes it needs to do, and they put in the specific material properties for different types of things. Everything's labeled and gathered. It's a lot more automated. So the EarthCARE mechanical model took around 2-3 hours to run. Conversely, the 8,000 node EarthCARE thermal model took around 24 hours to run. It's a lot slower. We don't have as many nodes either. So part of that is because a lot of it's done by hand. So we make a lovely, lovely image. This one here is Thermica. The major software that we also use in Europe is ESATAN, or ESATAN, depending on who you're talking to. That's that one over here. It's the European Space Agency Thermal Analysis Network. Catchy title. So what we do is that we make something that looks like the spacecraft. We don't need all the detail. We don't need all those screws in there. We don't need to have every single tiny faceted corner. We need something that is a good enough approximation of how much one surface can see another. So if you've ever sat in front of a fire, you're nice and warm, you get too warm, so you kind of move a little bit around the corner so you're not in its direct line of sight. So that's essentially how the heat's been moved around in a radiative exchange, is through that lines of sight. So that's what we're actually looking for out of this geometrical stuff. So we're looking for those lines of sight between one part of the spacecraft and the next. Also, how much each part can see deep space, because that's where the heat's going to go. Everything goes hot to cold. And where's the biggest source of heat on a spacecraft? Think of your summer holidays. Biggest source of heat, anybody? The sun, brilliant, yes. Yeah, so you've got the sun and then obviously the internal units as well, so all those bits of electronic devices. So that's roughly what we're trying to do, is understand where that heat's coming from. So the geometry is going to tell us different surfaces, but also how much each surface is going to receive sun. Nice and easy if you have a mission that's sat at one specific place compared to the sun and it's just there, which is pretty much what Gaia does. This one is orbiting Earth, so you can see which side the sun is on, the red bit. And so as they travel around, we're going to need to understand how that temperature profile, so that solar flux profile, looks over time. So that would be something like telecommunications satellites or anything on low Earth orbit, so International Space Station as one example. And then I've got this lovely thing here, which is this horrible diagram of all of the things. So I can't even read these, but I know what they are from practice. What you get is a box that is the mission box. This is where you title what your results are going to come out by, because you're probably going to run 40, 50 different cases. When you decide to batch run all of them, it's nice to know which one's which. And actually, yeah, at some point, that's what every single thermal engineer has done, is that they've not given them a decent enough name that you understand what it is that you've actually received out the back of it, and you end up rerunning it. And then you've got what your geometry is, which is that part. You've got what your orbit stuff is, that part, and then we'll also have the different particular software setups. Software setups for spacecraft are usually the setups for the Monte Carlo ray tracing, so that's pretty much what everything thermal has run on. Are you familiar with Monte Carlo stuff? Yeah, so a couple of nodding heads. So basically, in thermal land, what that is, for every single node, so each node is just essentially a square on the surface, it fires a whole number of rays in random directions, and then if it reaches another surface, there's a measurement of how much has reached that surface, and then we set extinguishing factors. So they're usually on percentages. If it's, say, above 10% of whatever's left, it's going to be reflected, and then we see how much is reflected to the next, As part of the analysis, we do a sensitivity analysis, which will be putting a whole load more rays in there. So instead of running 10,000 rays, we maybe run 100,000 rays and see if there are any significant changes in temperature. Significant change in temperature is anything within 1.5 degrees, which, if you think of solar orbiter at the front, which has a temperature range of around about 700 degrees, 1.5 feels quite tight to be able to measure it to. Yeah, so I think that's kind of enough about, well, that's roughly how the thermal stuff works. Does anybody have any questions at the moment? Not yet. Excellent. Okay. So the other side that we do, once we've generated all of our temperature data, there's somebody's phone on the desk ringing. So once we've used all of our nice thermal software to generate all of our temperature data, we've fed things back into architects, we've fed them back to mechanical people to understand if it's stable enough. Well, sorry, if it's going to work or not. Is we use something, this has come out of MATLAB. We use fairly standard software. It's not all about specialist software to understand what's going on. So all the different disciplines need to be able to talk to each other. This is something that the systems engineers would produce, and this is a stability requirement. So similar to what the Gaia stability requirement was in terms of how much everything points together, LISA Pathfinder had something very, very similar, and I'll have a look at that a little bit later on. Do you have any questions about how we do our software, or do you want to just start and look at missions? You blank faces. I'm going to start and look at missions. So, does anybody know what this one is? This was pretty famous last year and the year before that.
Is that one that landed on the Comet?
On the Comet, yeah. So this is the bit that landed on the Comet. This is Feely. Feely is about the size of a washing machine. And that was designed by, they were called DLR, and that's not the part of the London Overground section. No, that's German Space Agency. And that, yeah, about the size of a washing machine. And then the rest of it is Rosetta, which was designed, built, tested in the UK. Started off at Bristol, they moved it across to Stevenage, which is where I've been working for the last 6 years. And there was a lot of people there who worked on it, and when it came out of hibernation, there were a lot of fairly worried faces in case it had worked or not, but that tends to be how spacecraft work, is there's a lot of buy-in. So Rosetta was crash-landed into the Comet last year. It had a year of orbiting the Comet. That's the one that looks a bit like a rubber duck. Oh look, I've even got a rubber duck in the middle here. So that's the Comet. So one of the major issues that they had with Feely was it was a surprise what the Comet looked like. Everybody thought it was going to look like a potato, and then it wasn't like a potato. Did anybody follow the mission particularly closely? No. Okay. So Feely was pushed off the side of Rosetta, and it was always planned to be pushed off the side of Rosetta. And it had 3 feet and a thruster on the top. You can't really tell from a diagram. So the idea with those 3 feet is that it would kind of stick onto the thing, and then the thruster would fire to push it onto the surface of the comet while it screwed its feet in. Because while it's screwing its feet in, it's essentially pushing itself off again. And then the comet was a whole load more knobbly than what anybody thought it was going to be, and it struggled to get a grip. But also, before that happened, before it was actually jettisoned off of Rosetta, its thruster failed on its firing. So the decision was taken to run it anyway because we've got it all at distance. So this is where the software really comes into play on a spacecraft. If anybody is really into coding, you could become an attitude control, orbit control specialist. And what that software does is it will make a spacecraft do something like this lovely loop. So the software actually drove LISA Pathfinder in hibernation mode for 9 years. What that actually means by hibernation mode is we shut down as much as possible on the whole spacecraft so that it's doing the least it possibly can do to be able to conserve its batteries. As an idea on size, Rosetta is about this longer edge, is not quite 2.5 meters tall, and it's about 2 meters back. So it's not the biggest of things, but then its wingspan, its solar arrays are 32 meters. And that's because it comes all the way out beyond Jupiter to be able to catch up with the comet. In fact, we've actually picked it up. This is where it's come out of hibernation, and then it did this weird loop. And then we had the Comet Rendezvous. That was very exciting. Sat in a meeting room watching the data come in, and it comes in line by line of those first images of the comet once it's actually got there. But one of the major reasons a lot of people were particularly scared about Rosetta, if it's going to work or not, is that when it's on the launch pad, a lot of the blankets had to be taken off because it was too heavy. So it was too heavy for launch. And I said before that EarthCARE model took around 24 hours to run and had 8,000, 10,000 nodes, somewhere in that region. Rosetta was designed when we only had one computer per department, and we had 4 of the spacecraft on the books. So nearly all of it was done by hand. All of its calculations are done by hand, and you would book your time on a computer to be able to run overnight, and that would be your only time that you get to it. So the day before it's due to launch, there's the measurements, and it's too heavy. This is the easy part of what Rosetta did. It did a massive, great big flyby. Instead of going out towards the comet straight away, it went in towards the sun, and then it did 2 loops of Venus to be able to gain speed, comes all the way back out again, does a loop of Mars to be able to gain more speed, and then went out beyond Jupiter. And once it had left the orbit of Mars, that's when it went down into hibernation. So that's nearly everything being switched off. We got no more data back from there for another 9 years. And then when it did wake up, and that was will it wake up? Have we put enough alarms on this thing? All it did was just say, I'm awake. That was it. What do we do now? I'm awake. Once it had woken up and sent its little I'm awake, we sent it the next set of data of this is the test that we need to do. We need to understand what's still working, what's not working, because we've never really flown anything that far away before. We'd never had anything in hibernation for that long before, and we've ripped a load of blankets off on launch. So it might have got too cold somewhere in that. So that was kind of half the fun of Rosetta. And it all worked, and it was a huge success, at which point we then had to decide what to do next. So actually, a lot of the people involved on the mission the team had been ramped up, the software team had been ramped up 2 years before this hibernation. It wasn't preloaded with what was going to happen after it came out of hibernation, purely because we knew that software was going to change significantly in that time. We knew the hardware that was going to be available, so we can write specifically for what's going to be on there and what it needs to do next. So then it's woken up, it's passed all of its checks, and then we send a signal and hope that we're going to get something back within an hour. So it takes about 25 minutes to communicate with Rosetta, which means that it did all of this automatically from what somebody else has given it once we know the health of the whole spacecraft. And then in the same sort of way, that's when it managed to land Feely. That was exactly also on the same. It's been landed automatically. It's done that through the software. And then once Feely was landed on the comet, it was sending signals through the comet. So that was the point of Feely being landed there, it measured a whole load of things, like how hard is the surface. It took some images. That wasn't the main part of its thing. It was sending different radio waves through the comet, and Rosetta was orbiting it and picking up to see if he could understand what the structure was like on the inside, which is pretty impressive. Have any of you tried to do sending sound waves, or maybe ultrasound or X-ray, through a block? If you've done science, you might have done that one. And then you're trying to receive it out the back, and you're trying to work out where the holes is in something. It's something I did on my undergrad. That's really hard. They built a thing that can do that in space automatically all on its own. Yeah, that's some pretty impressive stuff. So we didn't have a whole lot of computer power either. The whole of the Rosetta model was 150 nodes. And when it came to we've got too much mass, we don't have time to rerun anything. We're just going to have to take off blankets and hope it works, because that was the bit that it was overmassed by. They took off about 5 kilograms, which doesn't sound like a whole lot, but it's enough to stop a successful launch if you're too far over, because things shake too much. So that's the joy of Rosetta. So that launched about 12 years ago. It was about 10, 15 years in the design. That's about 30 years ago. Does anybody know what this mission is? It's been on the news a lot the last week or two.
Is it the one that's gone to Saturn?
Yeah, so this is Cassini-Huygens. No, it's not. I'm lying. This one's been in the news a lot in the last couple of weeks or two. And this one's Voyager. So Voyager 1 and 2 are actually part of the Pioneer missions, which is why 10 or 11 are on there. And the reason this has been in the news this year is because it's turned 40. It's 40 years since it was launched. What did software look like 40 years ago? So I've no idea what on earth NASA managed to produce it with, but it still works. It's still sending back data. It's still sending back pings. It's still taking images. It's outside the solar system. It's been outside the solar system now for 3 or 4 years, and we can still communicate with it on a dish. I mean, the dish is a big dish. Actually, it's not that big a dish. I think it's 6.5 meters is the dish in diameter, which to be able to point something accurately enough is like it's there from so far away. So the software that's on board a spacecraft, they drive them a lot. I used to always get asked the question of, oh, do you work on human spaceflight? No, and I'm not interested in it either. Because you put something squishy in there and you've got a whole load more limitations. The squishy thing on a spacecraft wants an even tighter temperature requirement than what all those electronic boxes do. And they like to have air and pressure and some idea of gravity and water and food and all sorts of things there. You can do a whole lot if you have a pretty decent robotics setup. And these things aren't going to accidentally cut themselves and contaminate everything with blood or whatever else it is that's in there. So yeah, that is a Voyager mission. And do you want to have a guess at what this one is? So this is Cassini-Huygens. So Huygens is this little round dome thing. Often things that are going to be thrown onto another bit from something else are these kind of dome shapes. Beagle 2 was a dome shape. That's the one that got lost on Mars. Those that aren't up to speed. So Huygens is currently on Titan, and the reason that it's there is it was to look at Saturn's largest moon, and that's where they found evidence of water and liquid water. The moons are incredibly cold that far away from the sun, but because of how they orbit Saturn, there's a pressure differential because they're mainly liquid, and it's the pressure in the middle that is actually producing enough heat for it to be liquid water, which is potentially where there might be life forms from, which is why the decision has been taken to crash land Cassini into Saturn. So as an idea on height, this bit here is about 5.5 meters. Spacecraft aren't small, but it only had a long way to go. Look at all that. So do any of you remember this mission going up? I mean, I'm keen on space, so I remember these things bits of them happening or when it got to the next stage, when it started to get the images back. You might have seen some of the images, that some of the loveliest of images that have come back from Cassini are the essentially ripples within the rings. There's some videos that have been sent back from a spacecraft. And you can, NASA have them all on their website completely free, and you can just watch Saturn's rings, and they're not just rings, they've actually got ripples in them. It's where they think that actually Saturn doesn't have 64 major moons, it probably has more in the region of 400 or 500 major moons. Yeah, it's greedy on its moons. And that actually the rings are separate, there are discrete layers, so there are gaps. It's not just a great big plane of like the side of a dish or something like that. I always imagined it as being like a bit like a velodrome type thing. It's not, it's individual rings, and they're different densities. They've got different particulates in there. Some of them are more like micrometeorites. There's big chunks of dust, and there's all these moons, and there are actual discrete gaps. That's what we found out from this, and we control it from Earth. We can't really control anything from Earth. We can see what's going on, and then we can give it instructions to point at something else and to send us some data back. But it's a long way away. It's half an hour each way to send any data. For it to receive something, do what it's going to do, and then it's another half hour for it to come back. So it's definitely not in real time. So tomorrow, 1:30 in the afternoon, so many of these space things happen first thing in the morning, and it ruins your sleep schedule, I can tell you. 1:30 tomorrow is when it begins its descent into Saturn. NASA will have a live stream up showing the data as it comes back. It will likely be showing telemetry. It will show imagery for as long as it possibly can do. It will be showing some kind of particulate composition. It might not be your bag to go and watch absolutely every single one of them, but this is a pretty groundbreaking one. And Saturn is one of the big gas giants. It's solid in the middle, but what the pressure density looks like and how it can still hold itself together when it's that size, some kind of weird magic going on there. So this is my first thing in space, and it relates back to this very delightful graph. Everybody loves a graph, right? So this is LISA Pathfinder. It's a Pathfinder mission because it's a technology demonstrator. And normally we try and do all our technology demonstrators on the Earth because that's definitely a cheaper way to do things. But LISA is looking for gravity waves. So one of the biggest drivers of anything gravity-wise is mass. So LISA Pathfinder, as a technology demonstrator, is to demonstrate that we can detect gravity waves and that we can design something that's fine enough to be able to not interfere with whatever the measurements are. So I mentioned before the thermoelastic distortion. Any movement of anything is going to interfere with the instrument on this spacecraft. So the instrument is this bit in here. And it's 2 gold cubes. They're each around that sort of size. And they float. So that section in the middle is about that big. So you've got 2 gold cubes, and they're floating in free space with no interference at all from any other kind of masses around it. It's a whole load of mass around it. And then they fire, and it's firing lasers in between those 2 gold masses to see if there's any relative distance, any relative changes beyond what it is that we know about. What are the changes that we know about? Any temperature changes at all on anything on the spacecraft. If you change, so for any, I'm going to use a piece of paper actually. If that's part of my structure, its center of mass is in the middle. If I heat up one side of it, it's slightly changed shape. Its center of mass has moved. So its center of mass that acts on my instruments in the middle has moved. Every single item, down to the smallest little bit of screw, the last little bits of tape, that's a flat foil heater, various other things, they've all been weighed and they've all been measured, their temperatures have all been measured to understand how that's going to impact on its center of gravity as its temperature distribution changes, as its center of gravity changes. so that we can subtract it as noise from whatever else is going on here. And for some reason, it took quite a while to design this mission. Actually, the major issue that came from designing this mission was the propulsion system. How we got around thermally changing temperatures on the spacecraft was the spacecraft has the top of it is always facing the sun. So you don't have any random gradient across, say, if there's sunlight here and not over there, it's always sunlight on the top. The next thing is, whenever we're measuring the science, nothing is switched. So there are no changes at all in what is on or what is off during a measurement phases. So it means that you've always got the same amount of energy for whatever phase, which means we can be subtracting that energy out of the side of it. So that's actually heat coming out the side of it. So thermally, this was a bit of a challenge. So that's great. So we've controlled all those temperatures. But when you've got propulsion, as soon as you start firing, you've then changed the mass. And so you've changed what your center of mass is on the instruments in the middle. Gravity's ace, isn't it? So that's where the challenge of LISA Pathfinder came in. And actually, it's got electronic propulsion on it, so its whole effect, it's incredibly small changes in mass, and that's how we've got around it. And LISA Pathfinder has been an incredibly successful mission. In the next 10 years, touchwood, ESA will be commissioning LISA itself, which is gold cubes, again, of about this size, and each one is going to be 300,000 miles apart in a big equilateral triangle. So there's 3 of them, and measuring the relative change of distance between one and the next and the other one. So that's how we can start and measure the impact of gravity waves. And then we can find out all sorts of things about the universe. It should have probably be able to tell us things about black holes and the structures of the universe, because that's the next part that we can't see. It's a bit like, so we see everything in electromagnetic radiation. We can only see in certain wavelengths. Snakes see in infrared. We can use UV, so ultraviolet. We can even use magnetic fields to see how different things are interacting. Various planets in the solar system have actually been discovered because there's a funny wobble on another planet. But we can't see into the even longer ranges. Gravity has the longest range going. If we can see the impact of gravity waves, we can actually see even further back in time and further into space and see other structures that we simply cannot see in the kind of more standard electromagnetic spectrum. So that's the whole point of doing it. So that's LISA Pathfinder, all the software fun. And then this is the mission I worked on for the longest. This is Solar Orbiter. Solar Orbiter's up there. In fact, that is the thermal model there. And you can't really see a whole load of features of that. Solar Orbiter is a groundbreaking mission. It's the first mission that we've ever had solar imagery and solar plasma on the same box. So its box is about 3 meters by 2.5 meters by 2.5 meters. That contains absolutely everything it's going to do. So when I say solar imagery, that's images like this one. And you may have seen the same sort of thing in different colors, greens, blues, and with the solar flares. That's anything that's looking at the sun. Currently, the only solar physics that's been done has been from an Earth distance. So that is spacecraft, they're outside of atmosphere, but they're from an Earth distance. Solar Orbiter is going to be the closest thing that's ever been sent to the sun. It's going to be 1/3 of the distance from the Earth to the sun. Sorry, the close third from the sun. And so, of course, on its orbit, when it's on its launch, it's going to go the other way. It's going to go towards Mars first. And again, it's picking up the speed to be able to get it back into its trajectory. The major reason that we're doing that is actually when it's on its closest path to the sun, is that it's going to be traveling past the sun at the same speed as the sun's rotating. So instead of at Earth distance, you go, oh, look, sunspots. I wonder what's happening there. And then it's rotated around the corner. We'll actually be able to map it for a much longer distance so we can actually see how those different parts on the surface are actually interacting. And by having looked at it in all the different wavelengths, we can see how the different layers interact, because that's what the different wavelengths give us. We can see through. see through the different layers of the sun. The sun's got 11 different layers. And that's all, that it gives us another view to look at all that other solar physics that's happened. At the same time, we're also going to be measuring the solar wind, which, as it's never been on the same spacecraft before, it means that all that solar data that we've got and all the solar wind data that we've got, which is about 40, 50 years, we can look at all of that in a new light when we can see how they're interacting. The Voyager mission that's left the solar system, that is measuring the solar wind all the way out. We can actually look at the solar wind all the way out and see how those patterns have developed from what we've been able to see on the surface of the sun in terms of solar flares, black holes, and the worm structures. And that even ends up playing back into what we see on Earth in terms of the northern lights, or what the flares do in terms of potentially electrical surges. So it's all really good fun physics. And as if that weren't groundbreaking enough, the other thing that it's doing, which is what this orbit's showing here, is that it's actually doing, so we've got a couple of gravity assists. There's a VGAM, a Venus Gravitational Assist Maneuver, and that's to slow the spacecraft down. And it's going to come around Venus to slow it down so that we can actually start and change its angle. And the idea is that instead of just looking at the sun from the equator, which is lovely, we can start and look at it towards the poles, start and look at the polar regions. So that's, again, never been looked at on the sun before. And the reason that we want to do that is that's when the majority of all of its magnetic field energy is on its way. So that's Solar Orbiter. The Solar Orbiter main model is currently around 14,000 nodes, and that's just with reduced models for any of its particular units, so communications, its instruments, and a reduced model is 50 to 100 nodes. We got given a solar array. They told us they could only do it with a full model, and they gave us a left solar array, and it was 4,000 nodes. And then the model went quite a bit bigger quite quickly, and because we still needed it on the right-hand side as well. So we had to change all of them across and make sure that they still work, and that we built it correctly so that it wasn't being sensitive, because if it's flat onto the sun, they should both behave the same. And so it's another check that we can build into our modelling. We also have to test all these. They're built and then we test them in a vacuum chamber. And then we have to take our thermal model and make sure it behaves the same as the actual thing, so that then we can put it in our simulations of whatever it's going to do. And so we're not actually testing that the spacecraft itself can withstand what's going on. We're making sure that our computer predictions are real to the actual spacecraft, and then we can only simulate some stuff by analysis. So that's where the software comes in as being very useful. And then this is PLATO. PLATO is a mission that will look for Earth-like planets around other stars. So a really current and interesting project. And the reason that I've got two different structures is because it's still in bid phase. Don't know what it's going to look like yet. But it will have massive banks of cameras. And these banks of cameras have got a similar stability requirement to what Gaia has. This is the one that I worked on. From this side to that side, it's 5.5 meters long. Each of these cameras is pretty much about the same size as me. And the idea is that they all wobble together. So how it works is the different cameras all look at the same patch of sky, and you're looking for a particular dot of light and looking at it in all the different pixels, in the equivalent pixel on any of the other cameras. And if you've got a nice bright star, you get a tiny dip in that intensity of the light as you have a planet traveling across the front of it. And if you can measure it from a couple of different angles, you can actually see its periodicity. So the idea is that it's incredibly stable. And that's really, really difficult. We wouldn't have been able to do that at the same sort of time as we did Rosetta, purely because there's not enough data coming out of the models. Normally for a model in bid phase, we'd be looking at around 2,000 to 3,000 nodes. PLATO has around 25,000 thermal nodes, so that we can map it incredibly accurately to whatever's going on in the mechanical, so that we can produce all those stability graphs. So the software itself is a bit clunky. It's getting quicker. As computer processing power is getting quicker, we can make bigger models, we can do a lot more with them, but it means that we can do more crazy missions, and missions that simply weren't going to be an option however many years ago that was. I think I'm going to leave it there because I've probably bored you all enough with various different things. Does anybody know what this image is? Last guess. If I give you a clue, it's related to this mission. Yeah, this is the pale blue dot image that came back from Voyager 1 as it left the solar system. They were worried about blinding the telescopes, so on its way out the solar system, they didn't want to do anything funny with it, but then they turned it around to take a big image of the whole of the solar system, and that is Earth from the edge of the solar system. It's pretty small. So yeah, nice data from space. Right, I'll leave it there. Cool.